Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on January 23, 2026, just about 3 days ago. It introduces a massive new benchmark for interactive AI that reveals some harsh truths, finding that even today's best frontier models achieve only about 47% success in easy visual tasks and just 26% in harder ones. The paper is titled VisGym, Diverse, Customizable, Scalable Environments for Multimodal Agents. And, as we'll see later, the specific reasons for these failures, especially regarding memory and context, are really quite illuminating for the field. Over on Hugging Face, the VisGym model weights are ready for download. You will find the files and citation info to help you build these customizable environments for multimodal agents. Figure 1 lays out the scope of this new benchmark. On the left, you can see the grid of 17 diverse environments, covering everything from robotic manipulation, like pick and place, to abstract reasoning puzzles like matchstick equations. Then, the right panel illustrates the interaction loop using a 3D maze. The agent receives a goal, such as find the red dot, and must issue text actions like move or turn based on its limited first-person view. This setup forces the model to maintain memory and plan step by step, rather than just analyzing a single static image. So Figure 1 showed the breadth of tasks. Now, Table 1 compares VisGym to existing frameworks to highlight why this new suite is necessary. The top section lists benchmarks that are largely designed for evaluation only. They measure performance but lack the infrastructure to train agents effectively. In contrast, the lower section includes frameworks that do support training. VisGym, in the final row, distinguishes itself by checking every box. It supports diverse observations, partial observability, meaning the agent works with hidden states, and scalable data generation. Crucially, it enables both supervised fine-tuning and online reinforcement learning, providing a unified pipeline to actually fix the failures it diagnoses. Well, having established the framework, Figure 2 and Figure 3 reveal how today's models actually handle it. On the left, Figure 2 displays the success rates, where blue bars are easy tasks and red are hard ones. The frontier models in the middle, such as Gemini 3 Pro and GPT-5, generally falter, staying below 50% success on easy configurations. In contrast, the fine-tuned models on the far left achieve much higher scores, confirming that the tasks are solvable with specific training. Moving to the right, Figure 3 plots the distribution of steps taken for successful attempts. The pink curve for GPT-5 stands out with a long tail extending to the right, which suggests it is uniquely capable of managing longer context windows to solve complex, multi-step problems. Alright, while the previous charts show the averages, Figure 4 acts as the detailed scorecard, plotting success rates for every single task. The rows list the models, starting with the fine-tuned versions at the top. You can immediately see a stark contrast. The top 2 rows are largely deep blue, meaning these specialized agents handle most tasks with high accuracy. However, as you scan down to the frontier models like Gemini 3 Pro and GPT-5, the heat map turns predominantly yellow. Success rates drop to near zero for complex spatial challenges on the far right, such as Maze 3D, which confirms that general-purpose models still lack robustness. So, Figure 5 investigates a key reason for those failures: context management. This chart tracks success rates as conversation history increases from 1 turn to infinity. In the average panel on the left, notice the inverted U shape for the top models. Performance peaks around 4 turns and then drops with full history, suggesting models struggle to filter stale information. The effect varies by task, though. In matchstick rotation, GPT-5 improves steadily with context, while in the sliding block task on the far right, Gemini 2.5 Pro degrades almost immediately. Okay, moving on to Figure 6, which tests whether the primary bottleneck is seeing or thinking. This chart compares standard visual input shown in solid bars against a text-based ASCII representation in hatched bars. In the average panel on the left, notice the massive jump for GPT-5 in pink. Its success rate more than doubles when it reads text. This suggests the reasoning is sound, but visual perception fails. We see this clearly in the Maze 2D panel, where performance hits nearly 100%. Yet, the matchstick equation panel is an exception. Here, performance collapses because the complex ASCII art is actually harder to read than the original image. Wrapping up, the clear signal here is that current frontier models are surprisingly brittle in dynamic visual settings, often failing where text-based agents succeed. VisGym fills a critical gap by providing the scalable environments and synthetic data needed to bridge this perception-action divide. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.